Welcome everyone. In this session we'll dive into the smart home landscape. Not just the exciting technology behind it, but also the deeper implications for how we manage and interact with living environments. In this journey we'll bridge consumer IoT trends and the strategic opportunities they unlock for scalable digital twins in enterprise contexts. My name is Dieter Vermeulen, and I'm working as a solutions engineer for the AECO industry at Autodesk for plus 10 years now, covering the UK, Ireland and Benelux region. And you can ask me anything about stuff like digital twin, BIM in general, Autodesk AI, structural engineering, computational design, and many more. And this session is about using the smart home as a relatable, controlled environment to test real-time data integration, workflow orchestration, and visual feedback loops. Now, these same concepts like MQTT messaging, API-driven updates, and digital modeling, they will apply directly to buildings, campuses, or factories. The smart home is our test bed, the enterprise is our goal. Now, this is the principle I'm using to build up this story. We face a challenge, look for the solution, and then get to the outcome of it. And the basis of this story is, of course, IoT, or the Internet of Things. An Internet of Things describes devices with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the Internet, or other communication networks even. So the IoT encompasses electronics, communication, and computer science engineering. The agenda for this session looks like this. So first, I'm going to start with explaining a bit more about the smart home landscape. After that, we dive a bit deeper into the overview of the architecture that we are going to use for this solution. And then finally also get into the integration of the solution itself and getting a bit more into depth about how the technology can help you with this. And then we end with a few advanced use cases and see how data monitoring can help us to predict specific outcomes. Now, this part about the smart home landscape will highlight trends, challenges, and the opportunity space. Now, let's set the stage with where the smart home industry is heading. Now, smart homes are rapidly becoming mainstream, with over 400 million of connected homes expected by 2028. And this growth is driven by open standards like Matter, which ensure seamless interoperability across major brands, but also MQTT, which is a lightweight protocol for real-time messaging and stands for Message Queuing Telemetry Transport. Users now expect instant control over devices, whether it's lighting or HVAC, and that makes real-time interaction very essential. And then additionally, AI and machine learning at the edge, they are enabling devices to predict behavior, but also to perform maintenance without being dependent on cloud solutions. And amid rising energy costs, the smart homes are evolving into intelligent microgrids, managing resources efficiently to reduce costs and enhance sustainability. So these are a few trends shaping the future of smart homes, including AI, including energy optimization, but also smarter automation. And these technologies are driving a fundamental shift in how we think about connected living. But innovation alone is not enough. We need to bridge the gap between cutting-edge concepts and practical, real-world implementation. And this means transforming theoretical advances into tangible, everyday solutions that enhance comfort, efficiency, and safety. And a critical enabler here is data-driven decision-making. By leveraging real-time insights and predictive analytics, the smart homes can operate more efficiently and proactively address maintenance needs. However, As we move from innovation to application, we face new challenges. Managing diverse device ecosystems, integrating data from multiple sources, and ensuring real-time control, these are some of the key issues that need to be addressed to make smart home solutions truly scalable and reliable. So let's be honest about the current reality of smart homes. There are still key challenges. Device ecosystems are fragmented, and the brands, they don't always play nicely together. Data is often trapped into closed systems. Most setups are still reactive, not predictive. And too much manual configuration makes smart homes less user-friendly than they should be. Now, while devices have become smart, or homes themselves, they often feel disconnected. So where is this heading? As we look to the future, smart home digital twins, they will evolve far beyond simple dashboards. We are moving toward intelligent systems that are powered by AI and machine learning. And these twins will become more personalized, interoperable, and have more privacy consciousness by design. So this isn't just about gadgets, it's about building truly adaptive environments that respect user control and data ownership. Now you may ask, why are we looking at a smart home example in what is ultimately a B2B conversation? Well, because it's providing a proof of concept. The architectural principles and the technologies that we are going to use are directly scalable to facilities, campuses, or enterprise assets. And real-time data, predictive maintenance, and cross-platform interoperability, everything we've seen at home will be applying at scale. Now that we've explored the trends and potential of smart home digital twins, it's time to unpack how they are actually built. Well, the architecture, it consists of a few layers that are brought together into a digital twin. And on the left-hand side, we see the operational insights layers. So it consists of obviously a physical layer, which is our sensors and actuators themselves, and they need to communicate. So there is this connectivity layer above it, which is then also used for data processing as a new layer where the data brokers come in and time series databases ingesting the payload. At the other side, we also have contextual modeling. Contextual modeling is helping us to shape the twin building piece of the digital twin representation. And this is all coming back together in that replica of the physical environment, including data monitoring. Well, let's have a look at the first layer, which is the physical layer. Now, at the base of this architecture, we have the devices and sensors. So that consist of smart meters, motion detectors, thermostats, and some of these devices, they have built-in intelligence. And that means decisions can be made locally, like turning off lights when no one's home is a good example. And the sensors, they are the eyes and the ears of the systems. They are constantly sensing and reporting changes within the home environment. And to tie everything together, we use MQTT, which is this message queuing telemetry transport. And it's a lightweight protocol which is designed for fast communication. And each sensor is publishing its state to topics while other components subscribe to it. And this is decoupling the architecture. It makes it modular, it makes it flexible. And therefore, MQTT is not only ideal for smart homes, but it is also increasingly used in industrial and B2B IoT as well. And all this real-time data needs to be captured and structured. A time series data layer is supporting this ongoing monitoring and supports trend analysis for things like energy use or occupancy. And that's where this MQTT broker comes in. This one is going to accept all those messages and is making sure that everything is nicely structured in the way how it will communicate. Autodesk Tandem Connect will then act as a bridge between the broker and the digital twin in tandem so that it can digest all that information and send it back or send it through to the digital twin. And the communication between Tandem Connect and Tandem itself happens through Autodesk Platform Services. On the right hand side you can see a Tandem Connect pipeline that is bridging that data coming from the MQTT broker and sends it to Tandem. In the contextual model layer, we begin by authoring a high level of detail BIM model in Revit. And this is not just a conceptual design, it includes detailed manufacturer content that is representing real-world components. Now, this level of accuracy is crucial for effective digital twin scenarios later on. Once the model is developed, we will use Autodesk Construction Cloud with its module in Docs to manage the documents, to allow also multiple stakeholders to potentially collaborate seamlessly while maintaining a single source of truth. And Docs in here is used also to organize and control access to these models so that it's supporting a secure sharing and data governance. And by building such a detailed model and leveraging cloud collaboration tools, we ensure that the digital twin has this rich, accurate, but also a contextually relevant backbone for the twin. Now, all of this data comes together visually in that digital twin interface then. So this is like the top layer that takes all the rest into Tandem in here. So whether it's a Home Assistant dashboard or an Autodesk Tandem's 3D viewer, we're overlaying live data onto a virtual representation of the physical world. And that's where meaning is added. Now it's not just about temperature. It's the temperature in a specific room tied to occupancy, energy use, and comfort. Let's walk through a full end-to-end journey. A light is switched on and a Home Assistant is capturing the states. Then MQTT streams that data. Tandem Connect processes the payload from that MQTT, and the digital twin visualizes the change, and all of that happens within a few seconds. Now that we understand the architecture of this smart home integration, we can dive in a bit more deeper piece of this, which is the solution integration. And this chapter is covering the full journey of sensor data flowing from smart home devices into our digital twin environment in Autodesk Tandem. And we'll walk through the setup, the data ingestion, conversion, and mapping. And each component plays a vital role in enabling real-time contextual visualizations. This architecture shows the journey from raw sensor data all the way to insightful visualizations. What's key here is modularity. Whether you're managing a single home or a commercial building, this approach scales. And that scalability is exactly what connects this consumer-grade proof of concept to enterprise tools like Autodesk Tandem. We start with smart devices, which is the physical component generating live data. And these include sensors for motion, temperature, or light, as well as actuators like blinds, lights, and switches. And they operate locally and often communicate through protocols like Zigbee, Z-Wave, or Wi-Fi. And a key advantage is that their real-time responsiveness, especially when managed locally through platforms like Home Assistant. And they form the foundation of the data pipeline, pushing live operational data outward. And this is a general overview of how we integrate those smart devices into the system. So, of course, obviously, we need to have hardware and we need to set them up. So it could be with specific devices that we use for that. And then we integrate those devices into a control hub. In our case, we use Home Assistant for it. And once they are integrated in there, we get a collection of sensors. It could be device-specific sensors or some virtual sensors. And through a dashboard, we can control all of that. We can control the devices and review them. Let's have a deeper look on this specific flow. So the smart device setup itself. It can consist of wired devices for smart control of lights, shutters, and gates. But we also have Bluetooth sensors. Examples for that are door sensors, or wireless devices like an air quality sensoring device or smart plugs. And there are way more other network devices. So you can use maybe a Sonos audio system or a smart TV, a printer, everything that's actually placed on that network that is connecting with the edge gateway can be monitored. The control hub that we use for this particular case is called Home Assistant. It's an open source and free platform that is designed to control and automate the smart home devices. The advantage of it is that it's running locally, so you can install it on a device like an Android or a Raspberry Pi, and you can connect to it using mobile devices such as your phone or a tablet or your computer. It integrates with more than 300 platforms. In this case, we show an example where it's integrated with Shelly. And Shelly are a collection of actuators and light switches, such as these ones here. It delivers a few basic sensors already into it. And another one is Tuya, which is also a very commonly used smart home dashboard for it. So as you have multiple applications that are running on your smart home, it's very easy to, or very useful to have them all together into one platform, and that's what this control hub of Home Assistant is taking care of. Now another part is also the sensor definition. So we need to collect information from those devices and also potential virtual sensors. So the sensors, they can come with the device integration itself, or it can be coded as a virtual sensor. Look, on the left hand side we see device specific sensors from this smart indoor quality monitors from Netatmo. You get already some sensors that are telling you more about the humidity, about the noise level, the temperature in your room. So you have those basic sensors built in already. But in some cases you need sensors that are not integrated in your device. So imagine lights. If your smart device that helps you to switch on and off the lights doesn't have a power meter in it, then you can simulate that behavior by creating virtual sensors that are triggered in a template the moment the light is switched on. So in this case, the light is using a power of about 20 watt. So we measure the energy over time of 20 watt each time that light is switched on until it's switched back off. And then finally, the dashboard control within our control hub, within Home Assistant in this case, is useful to control the states of the devices and the sensors, so to review what is, for instance, the air quality in my room, but also to work in another direction so that you can switch on lights, or where you can change the temperature of the room, or you can even use it to see live feed of your cameras around the home. So this was the first part of this solution. It's the smart devices. The second part is about the messaging, and the data needs to be captured and transported, and that's why we use MQTT for, which is a lightweight messaging protocol, and it's ideal for IoT. So devices, they publish updates to what we call topics. It could be, for instance, cover/x1/position or sensor/room1/temperature. And these topics are organized hierarchically, so it makes filtering and routing very efficient. And the MQTT broker, it manages all that device communication. So let's have a deeper look on how we use MQTT in this solution. So first, we need to understand a bit more about what the MQTT protocol is about. Then next is setting up a broker, which is that central server that will route the MQTT messages. Third piece is getting a payload message. So we need to define the messages that needs to be sent out if something happens in that Home Assistant platform. And then finally, we can also verify the message, because it's not just about sending it out. We also want to check the format of that message to see if this will be a message that could be accepted by other backend systems. We start with the basics of the MQTT protocol. It's designed to be lightweight, makes it perfect for IoT applications where the bandwidth is limited. And central for that protocol is the MQTT broker. That one is very crucial in here, because this is the important part that accepts information from an MQTT client and then publishes that information back to another client or to a backend system. So the broker acts as the central hub for the messages. In our case, we use the broker from Tandem Connect, and the role is crucial for message routing and topic distribution, because without it, there is no way to efficiently manage the device communication. Now, let's have a look on how we set up that broker. In our case, we use the MQTT broker from Tandem Connect. And it's very easy to set it up. You just create a new one, give it a proper name, and then also add credentials to it, so to make the proper communication with the platform. You don't get the URL immediately, so it takes a bit time, so approximately like 5 minutes. If you refresh a few times, then you get this URL, which then can be used for later configurations of things such as Home Assistant, but also for the communication within Tandem Connect itself. So within Home Assistant, there is that integration called MQTT, where you can fill in the details of that URL that we just created, including the port and then also the credentials that were provided in there. Now, something else that is also very important is when do we send out that message? So we have that broker in place. Now we need to send information to that broker. And in our case here, there is some automations that are going to run, which we call time automated data. For instance, every 12 minutes, we send information about the room temperature to that broker. So it's actually publishing the state of a device to a specific topic. But there is also messages that are going to be triggered when the state of a device is changing. For instance, a light is switched on or off, or the gate is opening. And we use this on a group of elements so that we can do some loops around it, so that every device is definitely going to be taken into account for when sending that payload message. It's also important to understand that payload message, because the key aspect is also the format. We typically use JSON because it's structured, it's easy to parse, it's widely supported. And in our case, we use MQTT version 3.1.1. That's also an important thing to understand here. Another crucial part is also the data integrity. To ensure consistent routing and processing, we establish a topic hierarchy like home/sensor/temperature. The structure not only makes data easier to organize, but it also simplifies the topic subscriptions and later on. And the payload message for sensor streams in Tandem, it should look like this. We have a device ID, which is identifying the specific sensor or the actuator. And then there is also data, which is defining the name and the parameter values. And it's very important to respect the JSON format in here. So that means using the correct indentation, and also make sure that you have a correct use of the curly brackets. This is an example of the payload message for sensor streams that are defined in Home Assistant. And this is how it looks like in the YAML code of an automation routine. So we have the topic and the subtopics, there is a device ID, there is the name, and then there is also the parameters such as state, power, energy daily, which are the metrics of each sensor. Now, before moving forward, it's crucial to verify the message format and content. And in this case, we use a tool called MQTT Explorer to inspect the live data streams. We can see the entire topic hierarchy and inspect each message to ensure that it follows our defined structure. So this verification step helps catch formatting errors early so that we ensure a smooth integration later on. You can, by the way, download it through this link on the slide. So that was the second part, the MQTT. The next piece is the contextual environment. And we need to create a BIM model for that in Revit. Preferably someone or something with a high level of detail, or LOD. And we use manufacturer grade content to ensure there is geometric and metadata accuracy. So once finalized, the model is uploaded to the Autodesk Construction Cloud, from where it's shared with Tandem. And here you can see how this whole flow will look like. So there's a creation of the BIM model in Revit. There is a cloud model which is defined, which is needed also for centralized access, for having version control if needed. And then we also aggregate that as built model or even models in case to contribute data to it as well in Tandem, which is the third piece. And then the fourth part is where we verify the assets. So we tag the assets with a classification code, and this means that we can augment them with some extra data to it. So starting creating the BIM model in Revit is the first part in that, and the goal here is to capture the as-built environment accurately. So to do this, we have this high level of detail, and I'm using manufacturer content in there to make sure that everything is reflecting the real world condition in the best way possible. Now, once the model is finalized, we upload it to the Autodesk Construction Cloud. And this step is essential for centralized storage and also for the version control. And as you see in here, it's important to have a view which is dedicated for the digital twin. So this is obviously called digital twin. This view has all the elements enabled so that they also become visible in the digital twin. If not, then they won't be available in Tandem either. So once you set the publish settings, you can then save it as a cloud model. It becomes available in ACC. Then in here you can use the ACC viewer to review a few of the properties and see if everything comes in properly. So the digital twin view will be the one that we will use later on for integration. So the third step in our workflow here is defining the twin building. And this step consists of 4 sub-steps, hence the indication in green here. So this is a very detailed workflow, how to initiate the digital twin in Tandem. An important in there is that we have an asset template. So if not, then you need to define one. And that's where we configure the classification system, where we create the asset parameters and assign them to the classification system topics. Also, we need to create the facility then. So that's where we connect with the cloud model where we get the digital twin facility then. Third step in there is where we verify the data structure. It's actually checking the data structure that you receive from that BIM model and see if there are any inaccuracies occurring. And then finally, we tag the assets with the classification code so that we can augment it with additional data. So the classification template itself, it's based on specific classifications at one hand, or customized ones, or it could be based on uniformat or on OmniClass. And the customization happens through Excel. The one that we do here is based on the uniclass from NBS and added with some additional topics in there. So let's have a look on how we define that. So you in here in the tandem category drop down, you get those classes, and in here we have a uniclass one which is customized so that we can add sensor topics to it, which were not available in the NBS. We can create some additional parameters, define those parameters, but eventually I want to have a smart home template here. So I take that uniclass format, I go to some specific topics in there. So I take the classification, for instance, for door sets, and I want to create some I want to add some additional parameters to it so that we can augment my facility with additional parameter values, such as the current state of a door, for instance, and also its service manual. Now, once we have that template in place, we can also create a facility. It's even possible to assign the template afterwards to that facility, but it's always easier if you have it up front. In here, you select a smart home template, create and continue, and that's the step where we're going to connect with docs. That's where we have our cloud model stored called Smart Home 2025, and there we can choose for that specific view, which is called Digital Twin. So everything I explained previously, this is coming together here in the creation of that facility. Now, it may happen that some properties are not well set from within a Revit environment. So for instance, if we have a look at this device on top of the counter there, there might be some problems. So we can see immediately what happens if we use the filter and if we ask for every object that has not been assigned to a level. So this Sonos device has not been assigned to level 0, neither the table. And this is probably coming because we've been using copy pasting between several levels and we didn't indicate the scheduled level within the Revit model. The final step in setting up the digital twin is then also tagging the assets. So each component in the model is tagged with classification codes, which is based on standards like this OmniClass or the uniformat like I explained. And this tagging is enabling standardized identification, and it simplifies the linking of the real-time data later on to those specific model elements. So in here we also add documents so that it's easier to get a manual from a device or even a service service instructions for that device straight from within our digital twin. Now you can check the classification of each of the objects. So at the end of using or doing all the classifications, we notice here that there are a few doors missing classification code. So you can select those objects or you can use the inventory level even to see which ones are actually unclassified. And then in here in the properties panel, you can choose its proper classification system that you want to use for it. And once done, it's going to be extracted from the unclassified objects. It's also possible to use dashboards for that. Like in this dashboard, we can see that 97.5% of the structure is classified in a correct way. So there are a few objects that are still to be classified in there. Now that's an important piece here to understand. Now the next part is where we get into the sensors, and that's where the real work comes in. This is the data ingestion layer, and that layer is handled by Tandem Connect. We will listen to the MQTT topics and parse device messages into structured JSON payloads, and these payloads are then sent securely to Autodesk Platform Services, or also called APS, using the REST APIs. And Tandem Connect is where you map MQTT data to the asset fields by using reusable payload templates, for instance, that is simplified on board onboarding of new devices. So that's actually at the front end and the Home Assistant piece where we do that. But this layer will ensure then a clean and a validated structured data that enters the digital twin ecosystem. Now, how do we do this bridging? How do we get the data from MQTT through Tandem Connect to Tandem? Well, in this subchapter, we are going to focus on that. So we are focusing on that data ingestion layer. It's managed by Tandem Connect, like I said. So the process here, it starts with gathering data from that MQTT broker that we defined, and we parse it into those JSON payloads, which are then going to be streamed to Tandem. And we need to, in some cases at least, we need to convert that data to comply with the standards of Tandem, send that payload to Tandem, and then in Tandem itself, it's going to build the connections in an automatic way. And then it's up to us to classify those connections and make sure that we have a good configuration of the streamed information back in there. So once we have those connections built in, then we can link the data streams to the digital twin assets, which will make the model very live. And this is a detailed workflow of how we get that data and how we bring it. So it's consisting of 11 steps, which I'm going to explain you a bit more in detail in the next few slides. So the formatting of the payload is a very important piece to make sure that it's accepted by Tandem. And the first 7 steps are all executed within Tandem Connect, connecting also with the platform services, and that's where we built the pipeline to connect with the MQTT broker and send that information to Tandem. Then step 8 until 11 is about the connections within Tandem itself that are automatically generated, and in there we need to configure them and make sure that the payload data is also mapped to the proper parameters that come from the assets. So let's start with the data ingestion itself. So Tandem Connect can take data directly from the MQTT broker by subscribing to those predefined topics. So in here, we indicate the name, we indicate the host. That's what we need in here. So we open the MQTT broker back in here. So to get that URL, you don't need to copy the port or MQTT prefix for it. So it's only the host name that we need in there. And then as a port, we indicate that 1883. And also, very important, give the base topic, which is in our case, Smart Home 2025. So the moment you deploy the system, it will accept information from that MQTT broker. So it's actually subscribing to that topic of Smart Home 2025 and all its subtopics. So that means that every moment the MQTT broker receives information, it will come in this node here. And by opening the logs, you can see how the format of each of those streams look like. Now, step 2 and 3 is where we check the data format and where we convert it to the Tandem standard format that we need in here. And there is a simple converter tool in there, which is using some scripting to manage information and to reform the information. Now, what we have in there is that we have 2 data layers in the message coming in from Home Assistant. So once we deploy the pipeline, you can easily see it when we open up the logs, or you can refresh it in here. So the moment you take the data received, the received data is what comes in from the MQTT, and what we see in there is that we have 2 layers of data. And that's what we don't want to have in Tandem. We only want 1 layer of data. So that's the outgoing data structure that how it should look like. So this converter is making sure that we unnest one of those layers already. Step 4 and 5 is where we connect to the Tandem API. So to connect to it, we need a application on Autodesk Platform Service. So that means that we actually need to build credentials so that we can actually connect with the API of Tandem. So in this way, APS will be connected to the Tandem facility through this unique user creation that we are doing in here. So we have the client ID and a client secret, and which makes it possible to open up the Tandem API of that facility for Tandem Connect. Okay, then from the side of Tandem Connect, we also link with the Tandem APS app through the unique client ID and the secret. And we also will need the URN. So what we do here in Tandem Connect is creating this connector that takes that data from the converter then later on. We call it streams, for instance. We need to make sure that the data center is taking the EU one because that's where my facility is stored. And then in the same way, we take the client ID and the client secret from the Tandem app, or the Tandem APS app at least, that we created on Autodesk Platform Services. And the facility ID is actually the URN of the facility that we just saw. We want to add some time data. And here you see device ID and data is very important. And in our case, we only take a batch size of 1 because the payload that is coming in is not that big. We don't need to wait until we have 100 messages before we send it out. So once deployed again, we see that already some information, sensor data, is sent through Tandem. So in this case, the solar panels have been sent out, and the name of the sensor is defined by the device ID. Now, the final step is then building the connections within Tandem. And we define connections between the ingested data and the corresponding sensors. So when sending information through Tandem Connect and the connection is a new one, then Tandem creates it automatically. And each connection is tagged with a classification code. So it makes the stream parameters available for that sensor. And that's what we are doing in here. So we are adding specific parameters for the air quality monitor. So once you update the facility template and you go back to connections, then we can select our air quality measuring systems and give it the right classification. And there you see you have those stream parameters assigned as extra asset parameters to the connections. We also need to configure the connections, of course, because on the left-hand side we see the payload that comes in Tandem, and on the right-hand side we see what are the parameters that are defined by the template. So you need to map those two so that those values, payload message, that this is coming in the right way in the database here. And there you get the results of this. So by streaming it to Tandem, these values for those stream parameters are going to change on a regular basis depending on how much information has been sent through Tandem Connect to Tandem, or at least at what time frame we are using. And this structured approach will ensure that the data updates in Tandem will reflect real-world changes, keeping the model live and actionable. Step 11 is optional. We can also attach a Tandem Connect or Tandem connection at least to a host to have a visual reference, and that's what we call a stream pin. So for instance, this air quality of the office, we can assign it to a host, which is this object coming from the BIM model, and then this way the pin is immediately shown in that model. So you can go in your environment in there, and then you immediately see how all the sensors are acting. So for instance, in this case, this is the situation after we have hosted all the sensors in there and defined them. And you see those red ones, there are some green ones, depending on their status, if there is a warning or an alert. And this way you have an immediate visual overview of each of your sensors. So that's actually how you build the solution, right? So we just saw how we get from hardware configured smart devices to their representation in a digital twin using those pins. Now, what about if we go a little bit further and try to leverage all that information into a more advanced use case? And in this case, what we want to do is compare the digital twin and the device state and create some kind of a live environment of the digital twin when something is changing on a device itself. So what we want to do in here is sync asset parameters with real world conditions. So not necessarily the sensors itself, but the asset. So for instance, we trigger the state of a device in Home Assistant, let's say a light, and we want to get payload data from that device every time it triggers. And every time it triggers and sending that information, we want to reuse that information to update an asset property properly in my Tandem environment using Tandem Connect. Now, in our case here, we are going to use the asset parameter called current state. And it will reflect the real world condition, such as on, off, open, closed, mid, that kind of things. Now, firstly, we need to make sure that in Home Assistant, there is some kind of an automation that is sending a payload based on the state of an object. So in this case here, what happens is that every time a door or a window is opening, it will send that the information of that door and that window to the MQTT broker. So the MQTT broker is connected in Tandem Connect already, which we've seen in the previous steps. Now, the payload data that we get there for the streams is a bit different than what we need for updating the asset parameters. So that's why we have like this converter being used in there. So it's actually looking for every object that includes specific names like door, window, LT for light, Sonos, TV. And when it has those identifiers, which is created with the MQTT ID attribute of a device, then it will map them with the proper elements in my Tandem environment. So another part in that pipeline is the Tandem service. So the Tandem service is basically accessing Tandem through the Tandem API, which is made possible through Autodesk Platform Services. And one of the services that we have in there is update asset properties. So that's the data processing part that we want to do. So again, you need to complete the client ID, the client secret, the facility ID, and the same way as we've done already in our previous step. And then from there, we can build our families filter and also the asset filter. And the asset filter is a very important one in here because MQTT ID is a parameter used in Revit and also used in Home Assistant. And that will be our unique identifier for mapping properties and finding the proper object. So we actually are going to do an asset lookup and then compare and insert the values. So as you see in here on the left hand side, this is an example of how the attributes are defined in Home Assistant. So for one of the lights, the MQTT ID is called LT Dining Pendant. This is a very obvious MQTT ID, of course. It could also be some number that you use, a unique identifier, maybe even a GUID if you want. And then in Revit, we have this same data stored in there. So this is a bit of manual work that we've been doing, but still you can use it to compare Home Assistant with Revit, or in this case, it will be compared with the Tandem model, because this pendant triple bulb is of course also part of the digital twin, and that means that also its parameter stored in the identity data is also shown in the design properties of that object in Tandem in the category identity data. So that's why we have identity data.mqttid as an asset filter in our previous step. So let's have a look on how that works. Here in this video, we're showing how Tandem is used to visualize the state of those devices then in the real world. So here you need to have those parameters that are set into the proper class in your template, okay? And there is already a predefined view in here. So if you go to the living lights in there, and every object in there, so the ones that are in blue, they have a parameter assigned called current state, and that parameter is then later on used here in the filters. So what we want to do is on the right hand side use our Home Assistant, switch on a few lights, and this one above the table, that's the one that is showing live at the top right. The moment we click on that, also the state of the devices in the Tandem model is changing. So meaning that they color yellow, because in my filters I indicated that if current state equals on, show the object in yellow. If it's off, show the object in blue. And that's what the Tandem Connect pipeline that we just configured is actually taking care of. Now there are a few other examples that we can use in there, and we can even combine them in custom dashboards. Now, custom dashboards, it's still in a beta version, so you don't have it in the current version of Tandem as we speak today. So if you have a look at a few dashboards that have been created, there is, for instance, the one for doors and windows that we've pulled in here. And as you can see, the doors are colored in green when they are closed and red when they are open. We also see their current state on the left-hand side. And every time some changes happen in the real environment, so for instance, if someone is opening that door, it will send it to Tandem and that dashboard will change. We can also view the solar panels that we just saw, or also the position of the shutters, so that we can see if a storm is coming up, which of the shutters are actually open, which of the shutters at least are closed. Maybe we should open them to avoid damage by wind. So you can even couple this with weather data, or think beyond even that, couple this with weather data that sends you a message via Tandem Connect to your teams that you need to open your shutters, for instance. Another way of advanced usage is control your devices from within Tandem. Now this is a bit of a proof of concept. I'm not saying that we should use Tandem to control the devices of our house, but it is actually possible. So therefore we actually use webhooks. And let's go back to that same example of that pendant. So now the current state is on off, and if I click on that link, which is a webhook, it's set to on, and in Home Assistant you immediately see the result also coming coloring in yellow. And the same happens in the Tandem environment, because we have those filters set on, that if the current state parameter is set to on, then it should color in yellow. Or another example is even watching cameras. So for instance, above this gate, there is a camera which is also linked to a sensor that says that the status is clear, so there is no movement. Well, if we take that camera and if we go to the live feed, then we get an immediate view of the of what is actually happening in there. And yeah, we see that someone is coming in, so there is actually some movement there. Now, a final chapter in this story is where we want to monitor all that data that we just got in. So we showed you quite some use cases now on how we get the data from Home Assistant into Tandem. And we also want to monitor it now. So because once it's set up and once it's streaming the information to your digital twin environment, the only work you have is having a look at your streams and monitor everything what is happening in there, or even using color coding. And in this case, I want to have a deeper look on this door, the specific door 007. And we get a few charts of them, and if we expand, for instance, the status of it, then we see that at a particular time of the day, the door have been opened and closed, and maybe you didn't expect that. But even car maintenance, like let's have a look on the status of the car. What is the remaining fuel? What is the tire pressure? Or our vacuum cleaner? How does it look like for the filter? So what is the current lifetime of the filter, or the mop pad lifetime? So this way you can have a very centralized view on potential problems that might occur. And by adding thresholds to it, you get colors into your 3D environment, which immediately give you a bit of an alert if something needs to be changed before it actually breaks. So another way of watching the stream pins is, for instance, having a full overview. Like in our case here, let's go back to the office. And yeah, so this is where I'm presenting right now. So let's have a look at the color, at the temperature at least, which is coloring red, meaning that it's quite warm now. We can have a look on what is actually the temperature trend over the last month, and then we can see that indeed many times the temperatures have been rising, and that means that maybe we need to install an air conditioning unit or fix an existing air conditioning unit. And then another way of checking the sensor data is using heat maps, and this gives us a wider view on the whole level in here. For instance, in this case, I want to see the humidity, and this is showing the advantage of having the humidity of a room and not just what is the percentage humidity. We see it across the whole area, and in this last example we see also, and went a bit faster than I can talk, in this last example you can also see what is the current availability of our sensors, in this case door and window sensors. So they have a signal strength because they use Bluetooth, and here you can see that in a few rooms the signal strength is not strong enough, it's coloring red, so we might need to have a check if we need to replace the battery maybe in that sensor, or maybe there is something else going wrong that makes the signal very weak. So this was quite some examples on how you can bring this all together, right? And what we see in smart homes, sensors, messaging, analytics, visual interfaces, are the very same pillars that are used in scalable B2B digital twins. And by building on open standards and flexible architecture, the smart home becomes more than a consumer solution. It becomes a prototype for what is possible at scale in enterprise settings. And this architecture isn't just functional, it's forward compatible, it's scalable, it's built on protocols that are widely supported. And it gives you flexibility, whether you're prototyping in a smart home or deploying at least in a bigger facility, the logic remains the same. You're not locked into a platform or a device vendor, and MQTT and HTTP APIs, they give you full control. And this is exactly the type of structure that scales well into the enterprise digital twin space. So the solution is reusable across B2C and B2B applications. As we close out, let's focus on the key benefits of this integrated workflow. And the first is optimal building performance. Through this real-time monitoring and automated control, we are not only optimizing energy usage, but we also prevent costly shutdowns of equipment by having this predictive maintenance. Secondly, the improved environmental quality is ensured because we are continuously tracking critical parameters such as water, temperature, air, and the system makes automated adjustments to maintain safety and occupant comfort, whether it's controlling ventilation or regulating indoor conditions. And thirdly, the workflow significantly reduces energy consumption. By intelligently managing your resources and incorporating renewable energy sources, we are not only cutting costs, but also reduce the carbon footprint. So lastly, what I would say is that this entire workflow is scalable, repeatable, and by using the standardized communication protocols like MQTT is visual and intuitive, which makes the implementation straightforward and consistent. With this, I want to thank you for watching this video, and I hope you learned something from it and that you can reuse some of the components that we explained in here. Thank you, and see you next time.